Hello students, in this video we'll discuss how to solve constant coefficient homogeneous differential equations in the case where the characteristic equation has repeated roots. A homogeneous constant coefficient ODE has the form A y double prime plus b y prime plus cy equals 0. And in our last video we discussed how to write this symbolically with differential operators. Equivalently, a d squared plus b d plus c applied to y is 0. And last time we saw that we can factor this differential operator and use the fact that solutions of our essential ODE, y prime minus ky equals 0, where y equals c1 e to the kx, to solve the equation. However, in the case when there are repeated roots, we can't exploit the information from the previous video. Let's consider an example. Let's solve y double prime minus 4y prime plus 4y equals 0, or equivalently in our operator notation, d squared minus 4d plus 4 applied to y equals 0. And factoring the left-hand side, we see that this is equivalent to d minus 2 quantity squared applied to y is 0. If we tried to use the trick for distinct roots, we would have d minus 2 applied to y being equal to 0, and d minus 2 applied to y equals 0. Then, solving the far right part of the equation, in either of these cases, will both generate the solution c1 e to the 2x and c1 e to the 2x. So, by flipping the order of the factors, we don't gain any new information. So we need a new approach to solve this problem. What we will do is we will write the equation as d minus 2 applied to d minus 2y equals 0. Then we notice that we can make this entire expression 0 by making the expression inside parentheses 0. Hence, we would like d minus 2 applied to y to be a constant c1 e to the 2x. Because if we plugged in a constant c1 e to the 2x into the parentheses, we would have d minus 2 applied to a multiple of e to the 2x, and that would give me 0 by our essential ODE. So we've reduced our problem to the problem of solving the following ODE. We would like d minus 2 applied to y to be a constant c1 e to the 2x. Let me unravel this now and write this as y prime minus 2y equals c1 e to the 2x. This equation is now a first-order linear equation. Which means we can solve it by multiplying both sides by e to the integral of the coefficient of y. We will multiply by e to the integral of the coefficient of y, which in this case is negative 2. So, this will turn into e to the negative 2x. Multiplying both sides by e to the negative 2x, we have e to the negative 2x y prime minus 2 e to the negative 2xy is equal to c1 e to the 2x times e to the negative 2x. The terms on the right-hand side will now turn into 1. And our equation becomes e to the negative 2x y prime minus 2 e to the negative 2x y equals c1. By using the integrating factor, e to the negative 2x, the left-hand side now becomes a perfect derivative in the form of the product rule. This is equivalent to the derivative with respect to x of e to the negative 2x y is equal to a constant c1. Now we can integrate both sides. The integral of the left-hand side will be easy, since the derivative and integral will cancel, and it will leave me with e to the negative 2xy. When I integrate a constant c1, I have c1x plus another constant c2. Finally, I isolate y by multiplying both sides by e to the positive 2x. Doing so, we see that y is equal to c1x e to the 2x plus c2 e to the 2x, and we arrive at our solution.